Um, cool. It is recording and I'm screen sharing. So today we're going to be going over intakes and designing with gears slash belt slash chain. So, and first slide, pretty much these are just different ways of transferring motion from motors into another output, like a shaft or an arm or just anything really. So you use these in different situations. For belts, you're going to want to use at lower speeds with lower torque mechanisms. Chain, you would use in lower speeds and higher torque mechanisms. And gears, you would use in high speed, and they also work in low or high torque mechanisms. So between these two, you would want to use gears over chain if it's like a really if the things that you're moving are close together. So if your motor is further apart, you probably want a chain instead of a long line of gears. Also, something to note is that gears will move in the opposite direction as the motor that's spinning. So you would want to take that into account. Belts are pretty useful in intakes and just kind of making things move. So we like to use a lot of rollers in our intakes, but that we'll go over later. So belts are good for rollers because they don't have to go very fast. They're pretty low speed. Well, they seem to go fast, but they're pretty low speed and they're pretty low torque also because they just kind of suck in a ball. And you guys may not know it, but we actually did a chain design yesterday, or not yesterday, sorry, last time with the drivetrain because we were using it for moving the wheels. So that's how we spaced it. I used a different chain tool last time to distance them, but I'm going to show you a more general thing in a spreadsheet this time. So I would consider the drivetrain to be higher speed, but since the wheels are so far apart, we want to use chain instead of gears. So the chain you would probably use over the belts for the drivetrain because the drivetrain is a little bit higher torque. So you wouldn't want belts in that situation because they can slip. And the chain can also slip, but that's a whole different story. The CAD for belts and gears is really, really simple, actually, more so than you would think. So what you want to do is find the ratio that you want in between the belt and the gears, or sorry, between the two pulleys for belts or between the two gears. And I'll go in and I'll show you a little bit about what ratio means. So if you go on to, do I have Google Drive open? I don't. Hardware. So if you go into the hardware design folder in the 2020, 2021 Google Drive, which you should all be added to, you'll find this AMB design spreadsheet right here, which we use for a lot of different things, and also this JVN mechanical design calculator. These two, this one is kind of like this one, but a little bit more expanded. So we can just use this. And you can see down here, there's a bunch of different tabs for different things. There's a mechanism, gear ratio calculator. This one you have to think about a little bit, but if we go into this drivetrain calculator, which is what I wanted to talk about, you can kind of find out what gear ratio you're looking for or that you want to do. And this is going to lead into the project a little bit more. So this could also work for belts, but you would just kind of decide elsewhere what belt you wanted to use. So here we would go in and you want to select the motors that you have. They don't have Falcons on here yet, which is a little disappointing, because we do use those. We have a lot of them, and they're really cool. Right now, we'll just use sim, um, and we'll just go off of the sim ratios. The Falcons have, I think, a similar free speed and a higher stall torque. It's like, I think it's 4 Newton meters, or Newton over meters stall torque. Newton meters. I'm forgetting my units. I haven't done physics in so long, or since a few days ago. Yeah, then you want to go over here and select the number of drivetrain motors. We typically use 2. There's a bunch of different drivetrains. There's some 3-sim motor drivetrains, but really you just have 2 motors, and then they'll drive 1 gear, which you then reduce down. Or there's 1 pinion on each gear, and I'll show you that a little later. These are pretty much filled in. The driven weight, you want to put 100%, because 100% of the weight is going to be on the wheels. And then this robot weight, we usually estimate it to be the max. It could be a little lower, but we just kind of want to find out. The wheel diameter we talked about last time, sometimes we can make it 6, and you can see that puts down the thing. The wheel friction coefficient varies, but it's not too important, I don't think, unless you're doing like extreme calculations. But for us, it's not too important. So like,
how are you, sorry, real quick question. The blue cells are all input, but how do you determine what it is you want? Do you just discuss that with the design team?
Yeah, so typically you kind of just go with what your knowns are, and, or sorry, with the design team. Oh yeah, we're usually aiming for like a free speed of some amount. So you can see that the free speed's really high, 25 feet per second. Or
what's the free speed versus?
The free speed is like how fast the robot is going. Okay. These 135 pounds of robot are going when it's going at full speed. This is how fast the wheel's going. Okay. So if you had it like lifted up, that's how fast it would go. If it's on the ground, that's about how fast. So 22 feet per second. That's like really fast for an FRC robot, which makes it a little hard to control. So if we have it at this speed, we might want to put down the ratio a little bit. So instead of, or actually with Falcons, we use like an 8 pinion or 8-tooth pinion. So you see that brings it down quite a bit. So instead of a 12-to-60 ratio, we have an 8-to-60 ratio. And if you're wondering what the ratio is, it's like, so the motor outputs a certain amount of torque, and torque is like your R sine theta. I don't remember. FR sine theta. So
it's how much the wheel's turning.
Yeah, it's like the force of the turn, or right. So if you want a higher torque and a lower speed, you want to gear it down. So so it's going 8-to-60. So this 8-tooth pinion is spinning, say, at like 10 rotations a second or something. And then if you turned it into, like, it was an 8-to-80 thing, that would be a 1/10 gear ratio. Then it would only go 1 rotation a second and the outpitch shaft. But it would have higher torque, like 10 times the torque. Maybe? No, I think around there.
Well, you want higher torque for what reasons?
If you're lifting something heavy, or if you want to go fast, like you do here, or you want to shove a big robot, you would want more torque. So we play defense in the game. So it's kind of like a trade-off. If you go faster, you won't have as much like stability, or not stability, but like you can get shoved around a lot more easily. So like if a robot is coming at you with a certain force due to the torque of the wheels friction, and then you're here and your wheels don't have as much torque because the gear ratio is lower and you want more free speed, they're going to start pushing you, and it's going to be not fun because then you can't score.
Less resistance, right? Is that kind of what it is?
Yeah. So it kind of just shows you the final ratio here. And then from this, you can kind of play around with your CAD. This 8:60 is pretty common for us. Or like for all, if you're not sure what to do with your drivetrain gearbox, this is a good bet right here. And we're actually going to do it with Falcons, I think, this time. But they have not added those in here. I wonder if it's on the JVN. If you guys don't know what JVN is, he's like a mentor for which team was it? I don't remember. 148, I think. The Robo Wranglers. He was a mentor for them, and he made this design spreadsheet, and he works for Vex now, I think. I don't know his whole story. You can look him up. He's pretty cool. Do they have it on here? Falcon. Yeah. So
he just shared his calculations to first, and everyone can just use his calcs. Is that what it is?
sorry.
These calcs are things he shared with everyone. Is that, or is this?
Yeah, this is in a Google Drive. If you guys are on the Google Drive, it's in this area. It should be open to everyone. So
Right. But like he shared it with the team. Or
yeah,
he shares it with
so
everyone on.
let me see if
FMC.
I can find a path. So like, if you go into robotics main, and then 2020, 2021,
Mhm.
and then hardware, then design, and it'll be in this area right here. This is shared with all of you. I think if you put your Google Drive or your Google account into while signing up, you should be added onto here. So you would do kind of the same thing here. I want only 2 motors here, and then here I can change it from 8 to 60. And you can have multiple, and these are multiple stages here. That's why there's multiple. If you're not having multiple stages in a gearbox, you just want to put 1-to-1 for all of these so it doesn't change anything. Okay. High speed driving here. Okay. Yeah. I guess I'll explain what stages are. So if you put 2 gears together, then they'll be on top of each other. They'll make a ratio. Then you can put a gear on top of that one and then make it reduce another gear. That's the second stage. And you can even do that again with a third stage. And if you do anything more than that, well, I mean, you can keep going infinite times, but we typically do like 3 just to keep it easy, I guess. So anyway, this is heavy for a robot weight. Or is it? I think 150 is what like the max can be. And then, oh, right, and we had a 6-inch diameter last. It has more feet per second because of the Falcon. So if we put in 4 feet per second, yeah, we have 10.93 feet per second as our real life speed, or almost 11, which is pretty good. And then this amperage right here. So I actually don't know too much about electrical stuff, but you put like breakers on each motor output. And I think for the drive motors, we do like 40 amps. So if it goes up here, it won't really, I don't know. I think that it becomes problematic, or like, I wouldn't know.
That's when you go to the electrical team.
Yeah, that's when you ask Tavish, because I'm not the person to ask for that. But you can see like the difference between the Falcon and the Sim. If you note the free speed and the stall torque, it's like it's more free speed and more stall torque, and that's because it's brushless. And even more so than the Neo 2. This is like a pretty high stall torque, so you don't really have to reduce it as much. I don't know. But these are really good motors. They're also really expensive motors, so don't mess them up. Yeah. So did I have anything else? Oh, okay. I just wanted to show you how to CAD with belts and gears and chain. So in this calculator, there's also a chain and belt distance thing, I think. Well, in this one, I know there is. Chain and belt center to center calculator. So the one thing I don't like about this is that it's in millimeters. A lot of the times during the season, I went to just West Coast products. And then if you look up, I even have it like say belt calculator, they have it right here. So there's a bunch of different pulleys, and they'll show you how many teeth. And actually, I'll show you on Vex Pro the different pulleys. Motion, belts and pulleys. So there's two different types. There's these HTDs, which are for like thicker belts, and then these are GT2, which are for like thinner belts. And you can see the different, what's called the different tooth options, and you can kind of look through all of these. So there's 12 tooth, 16 tooth, 24, 36, and 48, and 60 tooth. And if you look at the drawings, I think there's hex bore timing pulleys. You can look at these, and this spreadsheet right here, or not spreadsheet, table shows you the diameters of the different things. So let's say I wanted to make a 12 to 48 ratio with a belt. So I would need a pinion first. So these pinions right here fit different motors. So it'll show you the bore. I don't really know what that word means, but it's like the size of the circle that it's going to press fit onto. This 550, it's not for the Neo 550, it's for the, which is a different type of motor that we use this year. Actually, maybe it also does fit with that. Yeah, actually, I think it does, but it was originally for the 550 Baron bots. I don't know. There was a team that made a motor, and it was called a 550, and it wasn't very good, but it's there if you want to use it, but you don't want to use it because it's not very good. There's bag motor 775 and Falcon fits, and the Falcon is not the same size as the Sim, so I'm not going to say it's the same size as the Sim, but let's say we want it to go to a 775. So what we would do in our CAD, if we wanted to make a plate, let's say, that you mount the motor onto, and then you want another, and you want it to reduce it right there. I'm not going to make the whole plate, but I'll just kind of show you how to do it. I need to shift some stuff around. Let's put this right here. Okay, so we wanted 12 to 48. So the motor, well, initially you want the motor drawing, so I'm just going to actually pull up another Vex Pro page and drag it over here. And then let's go to motor 775 Pro. And whenever you need dimensions, you can always come here. There's always drawings about stuff. So if you look at the motor, if you're just pressing it into a piece, this circle right here, the little extruded one, there's like the face, and then there's like the little circle that comes up. That's the thing that's going to press into the plate. So if we look at the drawing, we can see that that part right there is 0.689. It's really small, so I'll make it a little bigger. It's 0.689 inches in diameter. So that's going to be our actual diameter. Let's start right here, and we'll dimension it 0.689. Okay, so this is the part that's actually going to be pressed into the thing. And typically we like to have the 775 surrounded by metal, or just any motor really. You want it surrounded by metal when it's pressed on the thing. So we take also the diameter of the entire thing, probably, which dimension? I was just looking at it. Oh.
Over on the right?
I was looking at the wrong thing. Sorry. This thing is actually half an inch. Okay, so I was looking at this side. This is the electrical end. You're going to hook up your motors to that end. I was looking at this piece. It's actually this piece, which is 0. Maybe it is 0.689. I feel like I'm looking at the wrong dimensions here. This drawing is always just, okay. So this wide part here, oh, okay, never mind. I was right, 0.689. You have the plus or minus right there. So we'll just put that plus as a tolerance. So let's call it 0.689 plus 0.004, because we don't want it to slip out. And then I guess the distance, the difference between this tolerance here is like 0.005, which is within a range that we're okay with, because it's also going to be screwed in. Okay, now for the width of this whole face, it doesn't list it here, but it should be listed here.
There's a motor OD on the very right of the drawing.
Yeah. Oh, okay.
Got it?
The motor OD. Yeah. Okay, I was looking at the wrong dimension here. 1.744 inches. Okay. And we'll make this a construction line because we're not actually extruding this part. 0.744. And we don't need to tolerance that because it's not actually being extruded. So then what we want to do is look at our pulley dimension. And this is just for reference. We already have the circle here. So this is the part that we're cutting into the metal. And then for this part, we want the 775 press fit. So we'll take the outer diameter of that, and then we'll call it, okay, so 0.591. So it's going to be in here because this is the pinion. And a pinion is just a gear. It's the gear that you press onto the motor. It was 0.591, right? Okay. Yeah, it was. Okay. And now if we go into the hex board, we're going to 48. So the outer diameter would be 2.008. So we would draw that. I'll just make it horizontal for now. 2.008. And then what distance do we make this? Well, that is where the calculator comes in handy. So our first pulley is 12 teeth, and our second pulley is 48 teeth. And then what you want to do is have a desired, a lot of times when you're making this, it'll already be in a place where you need it to be like constrained a little bit. So you put in a desired center, and it'll kind of give you something close to that. So like right now, I can see that the distance is like 3 inches. So I'll call it, I'll say I want it to be 3 inches. And then the closest it can give me is, and this is number of teeth in the belt, not the pulley, 2.7149. Okay, so then we copy paste that. Was I already on here? Okay, make a dimension from here to here. And that is, oh, we also want this to be construction. Okay. And then what we can do is make our plate. Oh, I didn't add in the holes for the 775, which isn't as important right now, just for distancing. But I'll do it anyway, so that you can see. Okay, 631. So if you look on here, there's a bolt circle. If I zoom in a little bit, the bolt circle is 1.142 inches. So 142 inches. And then we'll add the holes. And what size are the bolts? Oh, it's metric. I'm guessing 9 screws. So they're M4 bolts. I don't really know what 4 millimeters is in inches. So can I put in 4 millimeters? Oh, I can. Okay. Okay, and I'll make these two equal. Okay. Oh, and also here, since this is going to spin on a shaft, we want a bearing here. And remember, our bearings are 1.125, and then we add a tolerance of like 0.00, like 3. And then that will distance it. And we can draw our tangent lines around it. I think I just made those. Oh, Yuta's here. Cool. What's up, Yuta? Okay. And then we can put our center point arc around it. Around these. Oh, that was not good. Okay. And now we have a plate that we can extrude. And we'll call it like an 1/8 of an inch. And we'll check that. So this would be like a plate that we can use. We would mount the 775 here, put on the pinion, and then we can put in a pulley and a bearing there, and then that would be a good reduction. I'll keep this here for people to look at later. Let me just make a new part studio. Okay, I'll close this, go back here. But you kind of just get this process where you go into those different spreadsheets or calculators, and you can find the distance between the two centers. Remember, it's always going to be center distance that it gives you, and then you just CAD it out. Okay. The next thing I wanted to go over was CAD for gears. It's kind of the same thing, but you don't really need a calculator for this one, so it's easier. You just want them to be tangent. Okay, so a little bit about gears. For every gear that you look at on VexPro or West Coast product, it's going to have this thing called the DP, which stands for diametrical pitch. So there's like 32 DP and 20 DP are the most common that we have on those, that we get from those sites. So that's going to mean like the number of teeth per inch in diameter. So the teeth have to be spaced the same so that the gears are able to mesh together. So, but that means it's pretty easy to find out how wide they are, and you don't have to look it up. You just need to make sure that the gear exists, pretty much. So we go into motion gears. You look at 20 dp half-inch X-bore gears. You have this long list, and all of these are like gears that exist. You can buy them. So, I mean, I can't because I don't have that much money, but I can take these different things. Okay, so we can say we have like a 22 dp, or sorry, a 20 dp gear with 22 teeth. So if it's 20 teeth per inch and 22 teeth, then how many inches wide is the diameter going to be? I guess that's like a question. Put it in the chat if you know. Pretty much just Marcus. Yeah, if you don't know, that's fine. It's just, you just put 22 over 20. It's just a calculation, so it's going to be a little bit over an inch. And that's going to be the width of the gear. And we'll make it that wide. And then we'll put our bearing, which is actually going to be the whole, let's call it 1.125. That, which is like just a little bit larger, but that's okay. So we just have to make sure to distinguish between these two circles. And then let's say we want that to ratio over to a, let's call it a 52 tooth gear. Or just a 50, actually, because I'm not sure if 52 exists. Oh, both of them exist, okay. So what we can do is we want them to be almost tangent to each other. This is also construction. So the teeth are going to be, this is the radius of the inside of the gear, and then the teeth poke out a little bit, but you want these to kind of, or sorry, it's not quite the inside, but it's like a little bit in. So when you put them next to each other, the gears are gonna mesh. So we actually want to tolerance these a little bit, and I use 0.002 because that's the number that Citrus Circuits uses when I look at their CADs. So I will do it too. And that's how you CAD for a gear. I won't make a whole plate here because we're about to make a gearbox. So yeah, let's get right into that. And remember, you don't want to use tangent tool to connect the gears because it won't let you distance it further if you use a tangent tool. It's going to make them just right up next to each other, which is a little too close. And then the gears can like grind. So today, we'll make, there's a chat message, for the 0.002 in the distance to the inner circle or the outer one. What? Oh, the one, okay, I think I get what you're asking. Okay, so this construction line here is the gear, and this, I'll actually just delete this because this is the bearing. That was the bearing. So when you're making a plate, you want the hole to be for the bearing, so you can press the bearing into the metal, because the bearing spins and you want the gear to spin also. So I would actually want a bearing here also. If I, it's like, we'll call these both equal, and then this one is 1, 1, 2, 5. You don't want these gears to be, you want these gears to be construction lines because you're not extruding anything for the gears. You're just going to be putting it there for spacing issues, because you wouldn't know how far apart these bearings need to be if you only had one of these gears. Or sorry, one of these, if you didn't have the construction lines, you wouldn't know how far apart they need to be. So look at that, used for construction lines. Okay. Did that answer your question? Or is it? Okay, cool. I'm going to start on the project for today, which is a gearbox for our drivetrain. And I'll rename this so plus drivetrain gearbox. Okay. I'll do it in another art studio, and we'll rename this to be gearbox. Okay. So earlier we determined that we wanted this to have 2 motors and an 8:60 ratio. So what we're going to do is just that. So we'll be working with Falcons, and I don't like going into Vex Pro to look at all the dimensions because I've pretty much memorized all of the dimensions, but I will do it just so I can show you where to find it. I was just here, motors, Falcon 500. So this is the amazing Falcon. They're really cool. Not CAD files, drawing. Okay, so here we can find the diameter, the bolt diameter, and the outer diameter. This is just 60 millimeters, which is what I remember. But that doesn't actually need to be the cut. So we'll put this out here, and we'll call, no, that's not what I wanted. Okay. This is going to be the outside of the first motor. We'll call it 60 millimeters. And then, actually no. What I want to do is make a line here. Let's just define it to some length for now. We'll make it like the height of the gearbox later because I want this to be in the center. Okay. So I'll put a circle here and make that construction. We can call it 60 millimeters. And then in this circle, I want another construction circle. And this was 2 inches for the bolt circle. And we get that here. So this is like 60 millimeters for the outside and then 2 inches for the inside. And then around the circle, we can put other circles. And it's 6 bolt holes. And these are 1032. So we have 0.191, which you can see 32 tapped screw set. And then what I want to do is circular pattern this around the center. Pull that here and call this 6. Check that. Okay, this is all good. And then what we want to do is CAD in this center motor press part, which is going to be 0.75 inches. And then we'll also put a tolerance on that so that it fits into the metal. So we'll call it, oh, that was actually really close, 0.75 plus 0.003. And you can find like books or something or websites about how to tolerance things correctly. I just usually go with a few, I guess, thousandths of an inch because it usually works. But I'm sure there's like a more exact science to go with it. Okay, groovy. So the next thing we want to do is put in our pinion on here. And we said in our thing we wanted a 8-tooth pinion. And the funny thing about these 8-tooth pinions is that they don't quite follow the DP rule. So it's going to be a 20 DP 8-tooth motor, or sorry, 8-tooth pinion, but it's actually going to be the size of a 10-tooth pinion. So it's going to be 10 over 20, which is 0.5. And if you know it's 0.5, that's fine. You want to put it as 10 over 20 because if you're going in to change it, then you can see how many teeth it is. Because if I just see 0.5, and I'm not very good at math, so I wouldn't quite know what the DP is going to be, or the number of teeth is going to be. Like if I wanted to change it to 12 instead, like what is this? I don't know. So I can change it. Actually, was it the same size as 10 over 20 or 12 over 20? I haven't done this in a while. Let's go to gears. 20 DP motor pinions. I want these 8 teeth. Oops. Drawing. Okay, this, all right, 0.5, right? So it's the same as the 10 tooth. Okay, cool. Next thing we want to do is put our second gear in there. So we said we wanted that to be 60 teeth. And since it needs to mesh with this 20 DP gear, or sort of 20 DP gear, I'll put it right here in the center, call it construction, and this is going to be 60 over, that was not the right thing to do, 60 over 20, and then drag this down. And then we want to make these mesh right here. So line distance, so it's 0.002. Then we have this. This can be a certain distance. Are these not? Wait, never mind. Okay. Next thing we want to, oh, that was the wrong thing. Next thing we want to do is mirror this over. And then when we move these, they move together. Cool. Then we can just set a distance for these. This part doesn't really matter, but I usually like to set it to like 0.3 inches, just so you have a little space. Cool. And then there also needs, or actually, you can set the distance based on, oh, that was not right, based on this bearing. So there has to be a bearing in the thing here. So this needs to be 1.125 plus 0.003. And you see these are just touching, so I might even want these a little bit more out. So like, oh, or actually, this doesn't really matter because the flange is going to be on the inside of the plate, and then it won't matter too much. Right. So if these motors intersect, then, or sorry, if they intersect with this part, then it wouldn't matter too much. And then we also need some standoffs so that you can distance the two plates apart. So our standoffs are typically like 3/8 of an inch, so 0.375, if that's right. We can put like 2 here and then 2 that go into these motor holes, which is something that I like to do. That was really big. So I'll call this 0.191 for the bolt hole. And then we can put it like a distance below. We'll say like 1 inch. And then we can bring it a little closer to the gear, but I don't want it directly interfering with it. So this is not the right dimension. Or or actually I can put it a distance from here, and I'll call it maybe 1.5, and then reflect it over this line. And ooh, actually, you know what I want to do? Let's put this stand up here, and then call this 0.3/8. Okay, that's still good. And then we'll also reflect that. Okay, so these are our standoffs. There's going to be like these kind of like tubes that go around the bolt, and it kind of adds support so that it's separating the two plates that are holding the gears. It doesn't matter too much where you put them, as long as they're not going through the gear right here, because then it won't work. And you might not understand what all this is right now, but when we put the assembly together, it's going to make a lot more sense. And then we'll also put a standoff like here, because I like to put the standoffs in the motor here, because it saves space, and you can just put the bolt through, and then it plugs the motor in, or doesn't plug it in. That's something different.
Do you have a picture, Ben, a 3D view of what a final gearbox? You have an image of what this is going to look like at the end, just so that
you
can follow what all you're doing.
Yeah, okay. So if I go into motion and then gearboxes, it's not going to look exactly like any of these, but I guess it's pretty close to this one. This one has 3 sims. This one, or the one we're doing, has 2 falcons. But you can kind of see how there's like, there's these pinions that are on the end of the motor, and they're going to drive this part. And this one has multiple stages, and these like black things right here are the standoffs that we're cutting. But the way that I'm doing the standoff is so that the plate has it on one side, and then the bolt just goes into the motor instead of being retained on the other side by another bolt. So it's pretty cool when we do it that way. Okay. And it's not going to look exactly like that, but pretty close. I actually don't need to put this here because it doesn't matter. We can actually put the stand up wherever we want, but okay. Now we can start. Am I missing anything? I don't think so. I think I kind of have everything here. Okay, now we can just start connecting it so we can make it an extrudable part. And then call tangent on that. And on that. Maybe something wrong with and then you also want it on this top. Oops. Just enclose all of this, and then you can also put lines here and make that tangent, and make this tangent, and then put a line, or I could just reflect that actually. Then I'll put some center point arcs. Okay, now this is an extrudable piece, and we can work with it. We typically use 1/4 inch metal for gearboxes because it's bigger and heavier and needs more structure, I guess. Okay, so we have all that going. Actually, I want to change something in the sketch. I don't want this to be there. I want it to be there, so it's not sticking out. But that's just a construction line, so it doesn't matter. Okay. Should I start the assembly? I wonder. I could, I guess. Sure, I'll start it. I'll call this gearbox assembly. Which probably isn't the name we would usually use, but whatever. There, and we're gonna fix this part like we're supposed to. Okay, now let's put on our motors. So if we go into MKCAD motors, or you could download the motor off of XPro, but that's a longer process, and I don't want to fill up my computer with random CAD. We'll take the Falcon. It'll take a second to load. Or actually, there is a simplified Falcon that doesn't have, it doesn't take as much processing power, which I like because it takes a long time to do stuff when you don't have enough processing power. This is a really long shaft. I wanted the short shaft. Actually, I think I did something a while back. I put it into our folder. Not this one. 2813 library. I think I put it in motor accessory. Yeah, here we. You want long shaft? Actually, maybe the long shaft is the right one. Okay. Oops, that was not right. Okay. Let's just keep it like that. We will mate this up to here, and then yeah, the holes fit. It usually knows how to do that pretty well. And then I don't quite want this. I could linear pattern it, but I don't have to. I'll just make another one. Put it on here. All is good. Okay. Now we want the pinions. Going to gears. Here. And we have this 10 tooth, which is not what we want. We want the 8 tooth. This one right here. And you can see it has like this different spline thing. So that's how you know it fits with the Falcons. So we'll just select the center mate connector. And there's some these like spacers that you can put on the Falcon, but those kind of, I don't know, you have to mess around with them a bit, and it doesn't really matter too much. So I'm just gonna not do those for now, but that's okay. This is so annoying to select. There we go. And put it here. I did that all right. Okay. Now we can put in a bearing. It takes so long to load. What we want is going to be a half-inch hex, this one, flanged bearing. So this flange is going to keep it from slipping out of the part. Select that face, put it right here, flip it, boom. Okay. Now we also want a little spacer here, and we can actually do that in the part studio. And I'll show you how to use the spacer tool today, I guess. So if we go, and the reason we want a spacer is just so that the gear isn't pressed up like right against the bearing. The gear also has some spacing, but it's just kind of good to put it a little more. It can even just be like a 16th spacer. Okay, so I'm gonna minimize this part. We're gonna use the.
Is that to reduce the friction between the gears and the bearing?
Yeah, I guess that also works. So we want this to be a half-inch hex spacer, and we'll call the internal outer like that much, and then the external diameter to be, let's say, 0.7. I think that's, yeah, I think that's how much I usually do. And then the length, we'll call it 1/16. The orange we'll put there. And then we have a little spacer. We go into our gearbox assembly. We can grab this, pull it out, and then just make it on right there. And it doesn't line up with the hex, which I don't like, but it doesn't really matter. So yeah. Okay, now we're gonna add in our last gear, MKCAD gears. And 60 was what we did, right? 60 tooth. And this one's pocketed a little, so I like to use it because it's lighter. We have that in there. Mate this part to this part. And you can see that the gears are in like the ideal space to be meshing, and they don't align like they would in real life, but that's not important for the design, because what we're really trying to design is this plate and the spacer distance. So that's why we put out all of these parts. Quite finished. I think that's as far as we'll go today. This isn't quite finished because we also need this end plate, which is actually going to be, we can just put it again for this plate and then space the parts out. And then we'll put this shaft and then connect it into the drivetrain. I guess that'll be all for today. I'll stop sharing my screen and also stop the recording. I was recording, stop.